Hello, in this video, we're going to convert a heat equation solver to a Burger's equation solver. So I've made a few updates from my heat equation solver. First of all, I've renamed the file to Burgers 1D from Heat 1D and changed the function file name. I've also changed here the equation that we're editing, and this is just for our own purposes so we can recall what we're doing. Normally, Burger's equation you'll see written with the nonlinear term on the left-hand side, but for computing, it's good to remember that we're going to put all of our terms on the right-hand side and compute in that way. There are some other methods where you might take, say, the linear term and treat this implicitly, putting it on the left-hand side, but for now we're just doing something fairly straightforward and say explicit. We'll just keep everything on the right hand side. Okay, so for our heat equation, if we recall, this looks something. If I run it, we just get a nice heat equation here. Notice everything just sort of melts down and fades away. I put a little timer up here with this this title button. And we're just seeing the heat equation get solved with a standard Runge-Kutta solver, which calls this right-hand side function. And all that right-hand side function is doing for now is multiplying the viscosity, nu, times the square of the wave numbers, times our variable, our input variable. And we have to input both of these, k squared and the new variable at each stage of the Runge-Kutta solve. Okay, I've also put this figure window style docked. That just makes it a little easier for me to record this so that the window stays docked on the screen, but you don't have to have that in your code if you don't want. Okay, so let's modify this to a Burger's equation. That is, we want to incorporate this nonlinear term. And at first, it's not immediately clear how we might want to do something like this. Maybe we would do something like go into Fourier space, but then we would need to know what the product looks like in Fourier space. And it turns out the product in Fourier space, well, you're taking a product of two Fourier series. So you have a multiplication of two infinite sums. That leads to a convolution. And convolutions can be very, very expensive because essentially every point needs to be multiplied. Every data point needs to be multiplied by every other data point in some sense. So it turns out keeping this term in Fourier space is, or at least computing it in Fourier space, is not a good way to go. A much better way to go is to go back to physical space, that is, take an inverse Fourier transform, and then do this multiplication. Doing it that way is sometimes called the colocation method because the data for u and the data for ux are both stored at the same point. So that is the same point in space, the same x value. So when we multiply them together, we're just doing as many operations, as many multiplications as we have grid points. For the for a convolution, it turns out we need we need to do number of grid points squared, roughly, multiplications, which is very expensive. Okay, so let's take a look at what we're doing here. What we need to do then is when we input this u hat, we'll need to convert it back to physical space. So let's do that. Right away when u hat comes in, we need to compute, let's just call it u, and that will be the inverse Fourier transform of u hat. But it's good to use since everything here is in real variables, we will use the symmetric tag just to make our computations a little more efficient and accurate. Okay, we also need to know what ux is, though. And to know what ux is, we will do it by computing the first derivative. The first derivative in Fourier space can be computed very accurately by multiplying by the individual wave numbers times ik. So I've just called that ik here. But of course, if we just write down here, so I could write something like maybe ux hat and call that ik times, of course I need to use the dot times u hat. If I do something like this, this should be enough to compute that derivative, but notice that our function doesn't know what ik is. So I can do this a few ways. I can just send it in, and then, so let's do that. So we'll have an ik in each of these spots. But notice this is starting to get to be quite a few arguments. And if we kept going in creating in making our function more and more complex, we'll have a very large string of arguments here. So I'll show you a way to compactify that shortly. But for now, let's concentrate on this. So here we've computed the Fourier coefficients of the derivative, but remember, that's still in Fourier space. So we should come back to physical space, and we can use the same type of operation here, just the inverse Fourier transform, but now we'll apply it to ux, something like this. If you want, in fact, it's probably a good idea to notice here we're computing these Fourier coefficients of the derivative, but we don't actually ever need them. So we could just take this ik times u hat and put it there directly without giving it a separate name. That is, without taking the time to store it. I like to align everything so I can kind of see what's going on. This makes it, for me, a little more visually clear. So now I have u in physical space and ux in physical space. And we can now just compute, let's say that we could call it the nonlinear term to be something like, well, it's on the right-hand side, so it's minus u, and then dot times ux. That's our nonlinear term. We can put this on the right-hand side and add, and there you have it. This is the this should give us a solution for Berger's equation. Now, there is a pretty important subtlety here that I'll discuss in a minute called dealiasing. So this is not quite the full solution, but let's see how it runs, and we'll take it from there. So if we run the thing forward, we're getting, it might be a little hard to tell. There's some slight motion in there. Let's take this out to a longer time, maybe time 50, just to see what's going on. And part of the issue here is that we have a very small, a very large viscosity. So this looks a bit like the heat equation. You can see there's a little bit of deviation from what we saw in the heat equation. But if we take our viscosity quite a bit smaller, notice that automatically adjusts my time step because my time step is being adjusted with the CFL condition. So we should then be actually able to run a little bit faster. What we'll see in this case is something happening, which is a little bit more interesting. I'm actually going to take the viscosity a bit larger. I'll talk about why in just a moment. So the viscosity here will be 0.006. Let's take a look at that. So again, we see a lot of the effects are really sort of dominated by that viscous term. Oh, no, I see what's going on. I've made a very silly error here. So this is why I like to code live, so you can see my mistakes. So can you spot what the error is? So we're not really seeing anything happening here. We're seeing a strange kind of spike here. And here I've got a nonlinear term, right? We've computed this in physical space. We've multiplied it in physical space. But then we just add it to the right-hand side. This bit is in Fourier space, and this bit is not. This bit is in physical space. So it doesn't make any sense to add these together. Of course, what I need to do is convert back. So I should write nonlinear term. I could do this a couple ways. I could write nonlinear term at is the FFT, the forward transform, fast Fourier transform of the nonlinear term. And I could put that right here. Or you could just do it directly. If you didn't want to keep track of the nonlinear term, you could put that here. There are many other ways you can do this. For instance, you can write the nonlinear term as 1/2 the derivative of u squared. That's fine. I'm going to keep it like this because I think it just follows a little bit more naturally from how Berger's equation is often written. But this is one way to go. We could also, instead of calling this separately something about the nonlinear term, we could keep this piece down here and compute in this way. It doesn't matter this is maybe slightly more efficient because we're not needing to store what the nonlinear term is. Anyway, let's take a look at this. This should give us something looking a little more like Berger's equation. There we go. We see a nice tilt, and then something kind of goes wrong. We see sort of an explosion there. So let's go back up top and see what's happening. So with Berger's equation, if the viscosity is 0, the equation will develop a singularity in finite time. It will blow up in finite time. But if my viscosity is too small in some sense for my resolution to be able to see it, then I can still get that blow up. It's as if it's sort of like 0 computationally. That is, we get a numerical shock showing up. So I can fix this in a few different ways. One, I can increase my physical viscosity, but maybe we have a fixed physical viscosity. This is something coming from physics or something like that, in which case maybe I don't want to alter the physical viscosity, and instead I'll do something like increase my resolution. So if I change from 2 to the 8 to 2 to the 9, that should double the resolution. If we run forward, we see something that's looking a bit nicer. And I don't think we'll see any blow up here. It's possible. It's looking, I think, pretty good. So now our resolution is enough, it looks like, to capture that viscosity. Okay, very good. So we should do a couple of things. One, it's nice to kind of visually check this out and see if things are going okay, but we should really look at this in spectral space to make sure things are going okay. The other thing is this dealiasing issue that I mentioned. So maybe I won't talk about this in enormous detail, but for now, let's do this dealiasing process. So for dealiasing, there's a great paper by Orsog. It's a 1-paragraph paper. He outlines how to do the dealiasing. But essentially, the idea is if I have something like if U is, maybe I'll write this in comments, if U is sine of x, then ux is cosine of x, if we take a derivative. But then if I take u times u sub x, right, then this will be sine of x times cosine of x, which is something like, I don't have it memorized, whatever it is, something like 1/2 sine of 2x, I think, something like that. The point is I'm going to generate higher frequencies. And so when we multiply coefficients together, I'm generating higher frequencies, and those are somehow no longer representable on my grid. So I should, in some sense, delete some of the higher frequencies after the, before and after the multiplication. So let's take a look at this. Really, one only really needs to delete them before the multiplication. So in order to do this, I'm going to cut out what are the highest frequencies. Now for MATLAB, the highest frequencies are sort of stored in the middle because the MATLAB first puts down the positive frequencies, then switches to negative frequencies. So we get the storage of frequencies in the middle. So to dealias, we'll start with our function in Fourier space, and I'll cut out those middle frequencies, something like this. So ceiling of n divided by 3 plus 1. N here is normally a power of 2, so ceiling divided by 3 is not an integer. And then we'll go up through, this should be u hat of all of this stuff, up through ceiling of 2 times n divided by 3. That should give us the middle frequencies. There we go. And we'll set all of those equal to 0, which we can just in MATLAB just set equal to the scalar 0. We have too many parentheses there. It doesn't like something. We have u hat of this. I need another parenthesis over here. Parenthesis here. Another one there. Set those equal to 0. So this will just select those middle frequencies and set them equal to 0. If you get this wrong because of the symmetry condition, so if you, for instance, used a floor or didn't have a +1 or something like that, you can end up violating the symmetry in your Fourier series, so that the inverse Fourier transform will actually be complex valued, and you can get some very nasty results when that happens. So just make sure if you're dealiasing, you're doing this symmetrically. So this is how we would kill those middle frequencies. But we actually need to do this every single time throughout the multiplication. So before we do any of this multiplication, we need to do this zeroing out of those middle frequencies. Notice now this, so I should put this dealiasing step here. So let's say we'll use, this is sometimes called the 2/3 dealiasing. We should put this dealiasing step here, but notice that we now need to, our function now needs to know what n is. So I could put in an n here and do that all the way down. But you see that the list of parameters is getting a little long. So rather than keep adding more and more parameters here, I like to do the following thing, which is I'll just package these all up in something called params, or sometimes I'll even just use the variable p. So I'll use something like this, params. And I just normally give it the same name. Params.ik will be ik, params.k squared will be k squared, and so on. So I'm just copying and pasting. This is a reminder here. Params.new is equal to new, and params.n is equal to n. The advantage of this, even though it's a little bit annoying to write all this in the first place, is that I can now just send params into my function, and I can add as many of these as I want later on. A different way to do this would be to use global variables, but using global variables can lead to a lot of problems when you're coding, because sometimes you don't realize that you're resetting it somewhere else. It's often best to just avoid global variables, but that would be another solution to this problem. The issue, though, is that I'll have to call all of these down here. So here I'm just sending in params, my parameters, but anywhere I see, an n or a new or anything like that, I will have to call it params.that thing, which is a little bit awkward, but maybe not too bad. So we got params.ik. I think that should be it. Okay. So now we can do this dealiasing right there in a single line. So our right-hand side function, as you see, is getting more complicated, but okay, we should be doing all right. First, let's do a check here. Stop and run again. And we get similar behavior to what we saw before. Great. All right. Well, this is nice, but it would be kind of nice to see, notice what's going on here. We're getting some type of, some rippling effects. If we continue to increase the resolution, so those are non-physical oscillations, but it might not be so clear how we know when this thing has enough resolution. So let's for instance, just so I can show you, I'll increase the resolution. Of course, this is now, this is 1024 points. In space. So every time through this operation, right, we're doing 4 Runge-Kutta stages. So that's, something like 4,000 of these operations. Each one involves 3 Fourier transforms. So this is now involving, something like, I don't know, many different Fourier transforms going on through these steps. And that's multiplied across the various time steps. So this thing is getting pretty expensive, and it's going to run a bit slower. A couple of ways we can speed this up. One way would be, well, we could pre-compute some of the stuff, like we could pre-compute these modes that we're going to dealias. I think that's not a bad idea. But for now, let's focus on a pretty easy fix, which is that we don't actually need to do this drawing each time. So I could do something quick and dirty like this. Let's say I'll only plot if the time step modulo 10, let's say, is equal to, well, let's see, I wanted to do it on the first time through, so I'll put equal to 1 there. and then end. So that means only every 10 time steps we'll draw. We should get a faster animation there. Right, so a lot of that time was spent just animating that figure. Okay, good. And we're seeing some of those non-physical oscillations kind of not appear now that we have higher resolution. Okay, good. But how can we be guaranteed? Maybe there's some, oh, there we see some tiny oscillations showing up right when we had that big shock. So one way to visualize this is to, instead of plotting every time the let me copy that and right. Instead of plotting everything what's happening in physical space, we can actually plot the Fourier transform itself. Of course, the Fourier transform is complex, but we'll only care about its magnitude, so the absolute value here. In fact, it's a little bit nicer. Instead of looking at this with a standard linear scale given by plot, a log-log scale is a pretty nice way to go. And our y limits here, well, our y limits are maybe a little bit less important. We'll go from maybe, say, 1e minus 20, that's 10 to the minus 20, up to 1e2. So 1e2 is 10 to the power, 1 times 10 squared, so that's 100. Our x limits here, let's just have those go from 1 up to, from 1 up to n divided by 2, which is that Nyquist frequency. Okay, and we can take a look at this absolute value as we go. So when we do that, we see that we're getting this rather large kind of nasty spike showing up here. Why is our resolution stopping there? N divided by 2 should be enough to show everything. Okay, what if we don't fix the x limit? Oh, I see. If we don't fix the, we're seeing the sort of symmetric other side of this. So, and we're plotting with respect to x. So our plot here should just be really 1 up to n divided by 2. You could do a floor of n divided by 2. So these are our x values. If you wanted, and then let's evaluate u hat just at 1 up to n divided by 2. See something like that. There we have something that looks a little bit nicer. I guess maybe we should go a bit higher here for these. Of course, the actual Fourier coefficients are these u hats divided by n. So let's divide by n, which gives us a little better picture there. And we're seeing something kind of funny showing up here. Let's see where that is. So if I take a look at the animation, if it'll let me click there, maybe not. Let's take a look at that dealiasing range. So I'm going to plot an x line at n divided by 3 and see where that shows up. So this is approximately our dealiasing line. Now, because of the Matlab indexing, there's really a shift by 1 here, but by one wave mode. But okay, so we see this line showing up here. That's happening right where that dealiasing is showing up. Okay, that's telling us that our simulation is under resolved. In fact, if we plot a y line at machine precision, so if I type just EPS here for epsilon, I get the machine precision value for a double floating point number. So that is, we should have our spectrum falling off. This is sometimes called the energy spectrum. We should have that falling off before this line. Oh, that was, yeah, there we go. We run it one more time, we see pretty quickly we're under resolved out there. Okay, so if we increase this a bit, let's say let's go a different route. Instead of continuing to increase our resolution, which would push this line to the right, let's decrease our viscosity and see how that goes. There we go. So we're seeing, so this is a picture of the absolute value, the magnitude of the Fourier coefficients. And we see that they're now, with this higher viscosity, they're dying off before this dealiasing line. So we're not committing any major violations here. This is looking pretty nice. Just to show you that we could have increased the resolution there. This will run a bit slower. Maybe we want to increase our time step here, maybe every 40 or something like that. So as we increase our resolution, we're getting something a little bit nicer resolved for a while, but then it sort of takes off. And so we can keep increasing our resolution until we have enough resolution to take care of. Notice that this line has now been pushed way off to the right. So there we go. We see a nice resolved simulation showing up. Everything looks beautiful. We get this decay in our simulation before we're hitting that dealiasing line. A lot of times you see people just showing the physical plots, and to me that's really not enough. When you're only seeing the physical plots, it's hard to tell if you're actually resolved. Our monitors are maybe few thousand pixels up and down. So really, if you're just going by the so-called eyeball norm, let's go back to physical space. You could have non-physical oscillations there that are smaller than, say, 10 to the -3 or 10 to the -4 that you're just not going to see. But with that spectrum plot using a log-log, you see it very clearly. So now we can have a lot of confidence that this is giving us a well-resolved plot. We were just looking at the spectrum there. We chose a resolution that's high enough to see everything is sort of lining up here. Of course, it's pretty slow because we are using this high resolution. So that's about 4,096 grid points. It's just running a bit slow. We could speed up our time here, plot less often. There are semi-implicit methods which could handle this in a nice way so that our CFL constraint is not so large, or so small in this case, I guess, forcing us to have such a small time step. But for now, we're at least getting a simulation that we can trust, which is pretty important. Okay, so we looked at, in this video, changing a heat equation to a Burger's equation. The basic idea is just to implement this nonlinear term. The fast way to do that is to go back to physical space by taking inverse Fourier transforms, computing the terms that we needed to, and making sure to take a Fourier transform to send everything back to Fourier space. So we're comparing apples with apples there. And of course, we need to do this dealiasing step first. Okay, great. So other than that, we were able to handle this with just a practically no modifications to I think we had 0 modifications to our Runge-Kutta algorithm, other than we kind of made things a little bit cleaner by packaging everything up into this params variable and storing everything there. Okay, great. We also looked at speeding up the plot a little bit using mod to plot every so often. There are other ways you can do this by using a set option, but maybe I'll show that when we get to 2-dimensional plots. And that's it. Yeah, so not too bad if you keep in mind these little tips along the way to modify your plot. And of course, looking at this in spectral space is vital to being able to ensure accuracy for your plot, so you can trust what you're doing. Okay, thanks so much.